South Atlantic Conservation Blueprint 2.2. How was it developed? Let's start with an overview. First, we divide the South Atlantic LCC region into ecosystems. This flowchart just shows 3 for simplicity, but there are 8 in total. For example, forested wetland and marine. We measure the overall integrity or health of each ecosystem using a suite of natural and cultural resource indicators. While this flowchart just shows a handful of indicators, some ecosystems have many more than that. For example, Pine and Prairie has 11 indicators, while marine just has 3. Indicators include metrics like riparian buffers, upland hardwood birds, and coastal condition. We use a modeling software program called Zonation to combine all the indicators for each ecosystem, ranking each area of that ecosystem according to its importance for the indicators. Next, we stitch together the zonation outputs for each ecosystem to produce a combined ecosystem integrity layer with balanced representation across all ecosystems. High ecosystem integrity scores translate into higher priority in the blueprint. Then we introduce connectivity by identifying corridors that link hubs. We use Linkage Mapper in ArcGIS to perform a least cost path analysis, optimized for shortest distance and highest ecosystem integrity score. Combining the areas of highest ecosystem integrity with the corridors produces version 2.2 of the Conservation Blueprint. Zonation is obviously integral to the blueprint process, so how exactly does it work? Zonation's objective is to conserve high-quality representations of all indicators. To do that, it looks at each ecosystem as a series of pixels, little 200 by 200 meter square units of area, and iteratively removes pixels that will do the least harm to all the indicators collectively. I say collectively because the algorithm ensures a balance across all indicators, so no one indicator falls through the cracks. Zonation chooses which pixels to remove based on a few simple rules. Let's start by looking at one indicator by itself. Here, each little square, outlined in gray, is a pixel. The blue shows the spatial extent of that indicator, and the yellow square is the pixel that zonation is removing. All else being equal, zonation removes pixels that are closer to the edge. It's not going to disrupt a beautiful intact core by pulling pixels out of the center, which makes sense ecologically. Given the choice between a pixel with a low indicator value and a pixel with a higher value, well, it's going to get rid of the lower value pixel. Now let's introduce some trade-offs between indicators. Let's say the blue square on the left is riparian buffers, and the orange square on the right is imperiled aquatic species. Riparian buffers has a much larger spatial extent, while imperiled aquatic species is more spatially limited and rare. So zonation is first going to remove pixels from the indicator with the larger distribution. Let's say we've continued to remove pixels from riparian buffers until it has the same extent as the imperiled aquatic species indicator. Now zonation is going to remove pixels from the indicator that has the least loss and switch to pulling pixels out of imperiled aquatic species. And that's it. 4 simple rules. Let's watch a demonstration of a zonation run for the upland hardwood ecosystem, sped up super fast. These red pixels are the first removed because they are least important for all the indicators. They become lowest priority in the blueprint. You might notice that these red pixels are clustering around major urban centers. That's because zonation is throwing out pixels with the lowest indicator scores, which are often in highly impacted areas. This process continues, prioritizing all the upland hardwood pixels based on the order in which they were removed, ultimately producing a map layer that assigns a relative integrity value to each pixel. These blue pixels are the last ones retained and become highest priority in the blueprint. It's hard to tell at this zoom level, but I should note that the blueprint does include some priorities in urban areas. Urban areas aren't excluded from the analysis. Now it's time to see how it all fits together. Remember the simplified flowchart you saw in the beginning? Well, this is what the detailed version looks like, listing every ecosystem and every indicator. Obviously, you can't read much of the text at this scale, but we're going to walk through how ecosystem integrity is calculated for each ecosystem, using maps available in the Blueprint 2.2 data gallery on the South Atlantic LCC Conservation Planning Atlas. We start with the South Atlantic region. The region is divided into 8 different ecosystems with defined spatial boundaries. Each pixel within the South Atlantic geography is assigned to one ecosystem. You might notice that the legend labels this layer Blueprint 2.1. That's because each layer is named after the blueprint in which it was most recently updated. Let's start with the upland hardwood ecosystem and move gradually toward the coast. If you recall, ecosystem integrity is measured by a suite of different natural and cultural resource indicators. For all the indicator maps, darker colors indicate better condition or higher scores. We'll start with the indicators that are specific to the upland hardwood ecosystem. This is upland hardwood birds, an index of habitat suitability for 7 bird species. Urban open space is an index based on the distance of urban areas from open space. Now we're moving on to cross-ecosystem indicators. These apply to many different ecosystems and will appear over and over again in determining ecosystem integrity. The freshwater aquatic indicators measure the integrity of rivers and streams. This is riparian buffers, an index of natural habitat surrounding rivers and streams. We're looking at the full extent of this indicator here across the whole region, but in the upland hardwood calculation, we're only considering where it falls within the upland hardwood ecosystem boundary. Permeable surface measures the percent of non-impervious land cover by catchment. Imperiled aquatic species measures the number of aquatic species in each watershed that are ranked as G1 or G2 or are federally listed as threatened or endangered. That's it for the freshwater aquatic indicators. Next are the landscapes indicators. These are intended to capture the connections across terrestrial systems. Low road density is an index of areas with few roads that represents habitat fragmentation. Low urban historic landscapes is an index of sites on the National Register of Historic Places surrounded by limited urban development. Resilient biodiversity hotspots is an index of mostly natural, high-diversity areas that are potentially resilient to climate change. That's all the landscapes indicators. Next, we'll look at the waterscapes indicators, which are intended to capture the connections across aquatic systems. We're still imagining all these cross-ecosystem indicators clipped down to the upland hardwood boundary. Network complexity depicts the number of different stream size classes in a river network not separated by large dams. Migratory fish connectivity is an index capturing how far upstream migratory fish have been observed. That is all the indicators used in the upland hardwood ecosystem. We run those indicators through Zonation and it provides this layer as an output, the Ecosystem Integrity Score. Look familiar? Each pixel in that ecosystem is now ranked on a continuous scale according to its importance for the indicators. The pixel with the lowest collective indicator value has the lowest score and was the first pixel to be dropped by the model. It's the darkest red. The pixel with the highest collective indicator value has the highest score and was the last pixel to remain in the model. It's a dark blue. Next is pine and prairie. We'll move more quickly now that we've walked through one. Starting with ecosystem-specific indicators. Regularly burned habitat is an indicator of acres of fire-maintained open canopy habitat. Pine and prairie birds is an index of habitat suitability for 3 bird species. Pine and prairie amphibians draws from the designated Priority Amphibian and Reptile Conservation Areas, or PARCAs, within the ecosystem. Now on to the cross-ecosystem indicators, remembering that we're only using the portion of the indicator within pine and prairie. So we add in the freshwater aquatic indicators, that's riparian buffers, permeable surface, and imperiled aquatic species, the landscapes indicators, that's low road density, low urban historic landscapes, and resilient biodiversity hotspots, plus all the waterscapes indicators, that's network complexity, and migratory fish connectivity. And Zonation gives us the ecosystem integrity scores for pine and prairie. On to forested wetland. Forested wetland extent represents the overall acres of forested wetlands currently present in the South Atlantic geography. Forested wetland amphibians draws from the designated Priority Amphibian and Reptile Conservation Areas, or PARCAs, within the ecosystem. Forested wetland birds is an index of habitat suitability for 6 bird species. Then we add all the freshwater aquatic, landscapes, and waterscapes indicators. And we have our forested wetland ecosystem integrity score. Freshwater marsh. Freshwater marsh extent represents the overall acres of freshwater marsh currently present in the South Atlantic geography. Freshwater marsh birds is a continuous indicator of patch size, plus all the freshwater aquatic, landscapes, and waterscapes indicators. And here's our ecosystem score for freshwater marsh. Estuarine is split up into 2 parts for the purposes of zonation, estuarine marsh and estuarine open water. Let's start with the marsh. Water vegetation edge is an index of edge length between open water and vegetation where estuarine waters meet wetland marshes. Wetland patch size, unsurprisingly, is an index based on the size of wetland patches. Coastal condition, as you see on this map, applies to both estuarine marsh and estuarine open water. So in the calculation for this ecosystem, we're using this indicator clipped down to the estuarine marsh extent only. This indicator is a continuous index of water quality, sediment quality, and benthic community condition that reflects the overall abiotic condition of estuarine marshes and open water estuaries. You know what's next: freshwater aquatic, landscapes, and waterscapes. And here's our ecosystem score for estuarine marsh. Now on to the other half of estuaries, estuarine open water. This time, we're using the coastal condition indicator clipped down to the estuarine open water extent only. This is the only indicator used in this system. Because only one indicator covers the estuarine open water area, it was not necessary to use zonation to prioritize this ecosystem. Instead, the ecosystem score is based only on coastal condition, processed to match the zonation outputs from other ecosystems so we can use it in the same way. Maritime forest. This ecosystem only has one ecosystem-specific indicator, maritime forest extent. It represents the overall acres of maritime forest currently present in the South Atlantic geography. Then we add freshwater aquatic, landscapes, and waterscapes. And here's our ecosystem score for maritime forest. Almost done. Beach and dune. Unaltered beach is an index of impacts from hardened structures like jetties, groins, and human infrastructure. Beach birds is a continuous index of habitat suitability for 4 shorebird species. Next, of course, are the freshwater aquatic, landscapes, and waterscapes indicators. And here's our ecosystem score for beach and dune. Last but not least, marine. Potential hard bottom condition measures the protected status or potential stress of solid substrate and rocky outcroppings on the ocean floor. Marine mammals is a continuous index of dolphin and whale density based on monthly density predictions for 10 species of cetaceans, also known as toothed whales, and yearly density predictions for 3 rarer cetacean species. Marine birds is a continuous index of highly productive areas for birds that feed exclusively or mainly at sea, using seasonal predictions of relative abundance for 16 species of marine birds. With that, we get the Marine Ecosystem Integrity Score. It's time to stitch all of these ecosystem integrity layers together. Starting again with upland hardwood, let's add pine and prairie, then forested wetland, then freshwater marsh, estuarine marsh, estuarine open water, maritime forest, beach and dune, and marine. Now we have the most important areas of each ecosystem in blue and the least important areas of each ecosystem in red, according to the condition of the indicators. Doing the analysis within each individual ecosystem and then seaming them together ensures the blueprint includes balanced representation across all ecosystems, so we don't prioritize one system at the expense of another. Roughly speaking, all the green and blue pixels are above average and make it into the final blueprint. The blueprint itself covers 50% of the South Atlantic geography. We reserve 5% of the total area for corridors, so that means the best 45% of the zonation output for each ecosystem makes the cut. The best 10% becomes highest priority, that's the dark blue. Then the next 15% below that becomes high priority, roughly the teal colors. Then the next 20% tier, roughly the shades of green, become medium priority. The lowest 55%, the reds and oranges and yellows, are not prioritized in the blueprint. But we're not done yet. We also have to consider connectivity. We perform the connectivity analysis in Linkage Mapper in ArcGIS. Linkage Mapper performs a least cost path analysis, creating corridors between hubs using the shortest distance possible, while also routing through areas with the highest ecosystem integrity scores based on the indicators. So how are those hubs defined? Let's start on the inland side. Within the South Atlantic geography, the inland hubs are basically large patches of areas with high ecosystem integrity scores and large patches of protected lands. To get our potential hubs, we combine the top 10% of the inland ecosystem integrity scores, which become highest priority in the blueprint, with permanently protected lands from the Nature Conservancy's Secured Lands database. But we also want our corridors to make sense beyond the South Atlantic geography, not create corridors to nowhere. So we add in areas with above average local connectedness from the Nature Conservancy's Resilient Lands project. We combine all those inputs, then keep all contiguous patches greater than 5,000 acres or 2,000 hectares. That gives us our final inland hubs. Now for the inland corridors connecting those hubs. To do a least cost path analysis, you need to define a resistance raster, a layer that determines how difficult or costly it is to move across the landscape. Within the South Atlantic boundary, resistance is based on ecosystem score. The higher the score, the easier it is for a corridor to move through that area. Outside the boundary, we again use the Nature Conservancy's local connectedness from the Resilient Lands Project, where high connectedness equals low resistance. As a final step, we wanted the corridors to avoid routing through heavily urbanized areas, so we set those as the highest possible resistance. Then we run Linkage Mapper and keep the best corridors to cover the 5% of the inland South Atlantic geography allocated for the corridors class in the blueprint. Keep in mind that many of the areas identified by Linkage Mapper as good for connectivity are also good for the indicators and are already prioritized in zonation, so the corridor class only includes areas that weren't already identified as highest, high, or medium priority. We also do a connectivity analysis offshore. The marine hubs are basically large patches of areas with high ecosystem integrity scores and large estuaries. The potential hubs include the top 10% of the marine ecosystem integrity scores and all the open water estuaries. Then we again keep as final hubs all contiguous patches greater than 5,000 acres or 2,000 hectares. We wanted to encourage connectivity between all large estuaries to the highest priority marine hubs. Once again, we need to define resistance to do our least cost path analysis. In the marine environment, resistance is based on the marine and open water estuary ecosystem scores, where higher scores are lower resistance. Then we run Linkage Mapper and keep the best corridors to give us the 5% of the offshore area allocated to the marine portion of the corridor class in the blueprint. Again, only including areas not already identified as highest, high, or medium priority. So we combine the corridors with the ecosystem scores, and that gives us the blueprint. The blueprint has improved steadily since version 1.0 was released back in 2014, thanks to input from the more than 500 people from 150 organizations actively involved in developing the blueprint. Nevertheless, and this might come as a shock, the blueprint still isn't perfect. That's why we maintain a list of known issues identified in the review process to help guide future improvements. Here's the list of known issues for Blueprint 2.2. This time we'll start in the marine environment and move gradually inland. Some marine areas in the far eastern part of the LCC region, particularly beyond the Blake Plateau, may be under-prioritized due to a lack of survey data for marine birds and mammals. Some deepwater coral areas that haven't been surveyed or mapped are likely under-prioritized. Investigation into an approach that combines known areas with suitability models is ongoing. Moving into the estuaries. Mouths of many priority rivers are under-prioritized where they transition into the estuarine ecosystem because they have poorer water quality and score lower on the Coastal Condition Index. Additional indicators for the open water parts of estuaries are under development and should help resolve this issue. The priorities for the open water part of estuaries are based only on coastal condition. Again, more indicators for the open water parts of estuaries are being developed. Now the freshwater aquatic known issues. Some aquatic areas, particularly smaller rivers and streams, are over-prioritized due to the sub-watershed scale of the Imperiled Aquatic Species Indicator. Some aquatic areas important for migratory fish are being under-prioritized in areas far upstream because the indicator does not fully capture historic distributions. Sections of some rivers seem to be under-prioritized, and investigation into this issue is ongoing. Now all the terrestrial known issues. Some forested wetlands are under-prioritized due to issues depicting both current and historic forested wetlands. Moving to a finer resolution approach to the blueprint in a future version should help resolve this. Important Carolina bays are often included in large patches of medium priority, but the bays and nearby areas should be higher priority. Different methods for resolving this issue are under investigation. Congaree National Park is under-prioritized, likely due to the forested wetland bird indicator under-predicting Swainson's warbler there. Some small patches of longleaf pine with good local conditions are under-prioritized. Ongoing efforts to improve fire tracking and develop a finer resolution blueprint could improve this issue in future updates. Some large patches of working lands are under-prioritized, particularly in the Big Bend of Florida, and improved working lands and patch size metrics are in development. For the Big Bend, using the Southeast Conservation Adaptation Strategy or CCAS blueprint, which combines the South Atlantic and Peninsular Florida blueprints, greatly improves this issue. Piedmont prairie areas are under-prioritized. A new indicator that includes some Piedmont prairie plants is in development. Urban open space is poorly captured in Georgia and South Carolina because the Nature Conservancy's Secured Lands database is missing many urban protected areas in those states. An update to that dataset will fill in many of these gaps. If you're interested in more detail than you saw here, check out the Blueprint 2.2 data gallery on the South Atlantic LCC Conservation Planning Atlas. From the CPA homepage, you'll click Access Blueprint 2.2 Data to visit the gallery. Here you can explore all the spatial layers used to create the blueprint. That includes the ecosystem maps, the ecosystem indicators, the zonation outputs, the connectivity analysis, and of course, the blueprint priorities. You can even overlay the blueprint with various threat layers to see how blueprint priority areas are likely to be impacted by sea level rise and urbanization. You can also download all the data into ArcGIS in one easy package by clicking here. If you want to learn more about the specific methods and data processing steps, download the Blueprint 2.2 development process. This PDF guide combines all the metadata into one report describing in detail how the blueprint was put together. Thanks for listening.